Hello everyone, welcome to my channel Physics with Bhatt. To learn concepts of physics, subscribe this channel and press the bell icon button to get notified for every new video lecture. Hello everyone, this is Bhatt once again with you with the new video lecture in the series of atoms and nuclei. In the last video lecture we discussed about the various concepts of nucleus, that is binding energy per nucleon. Today I brought another interesting and connecting topic, that is binding energy per nucleon curve. As the name itself clears the meaning of this, it is related to a graph. It is the graphical representation of variation of binding energy per nucleon with mass number. So mass number is very important parameter here. So we will have a graph between mass number and binding energy per nucleon. So this is the curve which we are talking about, binding energy per nucleon curve. On x-axis we have taken mass number and on y-axis we have taken binding energy per nucleon. You can see here the unit of binding energy per nucleon we have taken mega electron volt. So whatever values we are having on this y-axis, these are in mega electron volt. And since mass number is a number, so no unit is required. You can see the scale we have taken 50, then 100. So we have taken the interval of 50-50 on x-axis for mass number and intervals of 2 mega electron volt on y-axis for binding energy per nucleon curve. If you observe this curve minutely, then three regions are found here on the basis of the binding energy per nucleon. So let me share these three regions. The first region is mass number less than 30, that is A less than 30. So this region is A less than 30. Another region is the middle region, for which we have taken mass number greater than 30 less than 170, and the third region is mass number A greater than 170. So on what basis we have selected these three regions of this curve? The criteria of selection is binding energy per nucleon value. You can see in both heavy and light region, that is A less than 30 and A greater than 170, the binding energy per nucleon is quite low. In the middle region, that is A greater than 30 less than 170, the binding energy per nucleon is almost maximum. You can see from this line, it is almost a straight line. So we can say the binding energy per nucleon in this region is approximately or almost constant. So these are the three important regions we have selected. So let me list the main features of this curve. The first, we can conclude from the previous discussion that binding energy per nucleon is practically independent of mass number in the middle range, that is A greater than 30 less than 170. As I told you just now that in the middle region binding energy per nucleon is almost constant, so we can say it is independent of mass number in this region, and it is found maximum for A is equal to 56, that is Fe56, and this value is 8.75 mega electron volt. This is our reference and we are comparing with this maximum value 8.75. The binding energy per nucleon is low for both light nuclei A less than 30 and heavy nuclei A greater than 170. We just seen this particular aspect of the binding energy per nucleon curve, and on the basis of that we have divided the curve into three regions. What are the conclusions we can draw on the basis of these observations about the binding energy per nucleon curve? The first conclusion we can draw is the force between nucleons is attractive and sufficiently strong to produce binding energy of few mega electron volt per nucleon. The second conclusion we can draw, the constancy of binding energy per nucleon in the middle region, that is A greater than 30 less than 170, is the consequence of the fact that force between nucleons is a short range force. It means if the distances are less than certain region distance, then also the force is weak. If distances are more than the certain value, then again the force is weak. This conclusion we can draw from the middle region. Now we focus on the two regions, that is A less than 30 and A more than or greater than 170. So if we talk about the heavy nuclei lying in the third region, that is A greater than 170, then a heavy nucleus splits into two light nuclei of middle range to acquire stability and energy is released. This process is termed as nuclear fission. Likewise, we have the same kind of happening in the light region. Two light nuclei combine to form a heavy nucleus of middle range to acquire stability, and in this process also energy is released. It is termed as nuclear fusion reaction. So we have four conclusions based on the observations of the binding energy per nucleon curve. Let me share one more important part of today's lecture, that is potential energy of pair of nucleons. This is also quite helpful to understand few more things about the force between nucleons. So first we will discuss the curve. We will talk about what else we can say about the force between nucleons. This graph is plotted between the separation between two nuclei and the potential energy of the pair of nuclei. So this graph is potential energy on this graph is plotted between the separation between two nuclei and potential energy of the pair of nucleons. On x-axis we have taken the separation in femtometer, and 1 femtometer is equal to 10 power minus 15 meter. On y-axis we have taken potential energy, and again it is in terms of mega electron volt. If you observe this graph, you can see here the value of potential energy we have taken between minus 100 to plus 100. The minimum value is minus 100 and maximum value is plus 100 mega electron volt. Distances are taken in the intervals of 1 femtometer. From this graph it is clear that the potential energy is minimum at this level, and it is denoted by R naught, and it is almost minus 100 mega electron volt. As the distance between nucleons increases, then the potential energy approaches to 0 for more than 2 femtometer separation. Likewise, on the other side, if distance is less than R naught, then potential energy suddenly becomes positive. And we know very well that if potential energy is negative, then the force between the two objects or particles is attractive, and if potential energy is positive, then nature of force is repulsive. So what conclusions we can draw from this curve's observation, that we will list here one by one. For a separation greater than R naught, the force is attractive as potential energy is negative. As I told you just now, that if potential energy is negative means the force is attractive. The second conclusion we can draw, for a separation less than R naught, the force is strongly repulsive as the potential energy is positive. That I also discussed with you. Since in this region R distance less than R naught, then potential energy has become positive. Force between two nucleons falls rapidly to 0 if their separation is more than few femtometer as the potential energy approaches to 0. That also I told you, if the separation is more than 2 femtometer, then potential energy is found to be approaching to 0. So these are the main features of this curve, and what conclusions we can draw on the basis of these features about the force between nucleons. The force between the nucleons is known as nuclear force, and this force is found to be effective only within the nucleus. So let us list about the properties of this nuclear force on the basis of all the discussions we had gone through just now. The first property is the force between nucleons within the nucleus is known as nuclear force. So this is the name given to the force between nucleons within the nucleus, and it is nuclear force. It is a strongly attractive force that binds all the nucleons within the nucleus. So what is the role of this force? This nuclear force keeps all the nucleons within the nucleus, that is inside the nucleus. So one interesting fact about this force you will come to know. We know that the same polarity charges repel each other, and inside the nucleus protons are present and they all are positively charged, so they should repel each other, but because of this nuclear force, they are not able to repel, and they are not moving out of the nucleus. So it shows that this force is much stronger than electrostatic force between nucleons. This is another property of nuclear force we can list here. It is independent of charge and same between proton-proton, neutron-neutron and proton-neutron. This is the distinguished property of the nuclear force if we talk about the electrostatic force. So electrostatic force depends on charge, but this nuclear force is independent of charge, and it is same for proton-proton, neutron-neutron and pair of proton-neutron or neutron-proton. It is short range force and effective within the nucleus only. From the previous discussions, based on the two graphs, this is the very important outcome we can list here. Nuclear force is a short range force and it is found to be effective within the nucleus only. There is no mathematical formula for nuclear force. We have the mathematical expressions for all the forces like gravitational force, electrostatic force, but there is no such mathematical relation or formula for nuclear force. It is found to be repulsive if distance between nucleons is less than 0.8 femtometer. We had seen from the previous graph between the separation and potential energy pair of nucleons that if the distance is less than r naught and that r naught is 0.8 femtometer, the force becomes repulsive. So we can say the nuclear force has both attractive and repulsive nature, and these are helpful to maintain the spherical shape of nucleus. How it is related to the shape of nucleus? It's very easy to understand. The attractive force pulls all the nucleons within the nucleus, and repulsive force does not allow them to come closer beyond a certain limit. So in that way, two forces are present within the nucleus, attractive and repulsive force. As a result, the shape of nucleus remains spherical. So in this video lecture, we discussed about the binding energy per nucleon curve, main features, conclusions. Then we discussed about the potential energy curve for the pair of nucleons and the properties of nuclear force. I hope this video will help you to learn these concepts. Thanks for watching this video. We will meet very soon in the next video lecture. Till then, keep watching, keep learning.